So electrostatic potential means we already discussed, right? So what is potential means? It is the amount of work done needed to bring the unit positive charge from infinity to one point. Okay, and I said the charge is source charge Q. Okay, Q is the source charge. Okay, and you are bringing a unit positive charge from infinity, one unit positive charge from infinity to one point. For example, I will bring from infinity to the point A. This is point A. Okay, and again from point A, if I want to bring to the some point B, you just see here, this point A and point B, they are at in the field, correct, right? They are in the field. Which field? Source charge field. They are in the source charge field. So I can write like this. Okay, I also derived in the last class, right? Now, so whenever you want to bring the unit positive charge from infinity to point A, okay, till this place, till this position it's fine, correct, right? But after this, in the vicinity of this region, you need to do work. Okay, why we need to do work? Because electric field is in this direction. Electric field is in this direction, right? Electric field due to the charge is in this direction. You need to bring the unit positive charge against that electric field, so that you need to do the work. Okay, if you bring the positive charge against the electric field, how much work you need to do? The work done for the charge, how much it should be? It should be, work done should be equal to the, how much electric field strength is there, that much. Okay, so work done is Q into E. Work done is Q into E. So this is what we discussed already. And you know, again, if you want to bring from point A to point B, which is at a distance R, okay, again you need to do, so the work done from again A to B, A to B. How much we got? Last class we discussed, right? A to B. How much you got? 1 by 4 pi epsilon naught Q divided by R. Yeah. This is the electrostatic potential. So what is the potential means? Potential means it is the amount of work done to bring the unit positive charge near the vicinity of the source charge. Okay, so that whatever charge you are bringing, no, it should not disturb the source charge, because we are bringing the test charge. The test charge should not disturb the source charge. This is for testing. But actually speaking, whenever you want to find the potential due to multiple charges, system of charges, then you can bring a multiple charges near to the source charge, where you can see each multiple charge whenever you are going to bring, no, that time you need to work individually, correct, right? For example, if you want to bring one charge near this charge, for example, I will bring charge Q1 near the charge Q. Okay, so I will bring near here. I'll just write here. You just see this Q1 I will erase. Yes. Now I want to bring the charge Q1 here. From here, somewhere, if I want to bring the charge Q2 from some other point, if I want to bring the charge Q3, see, everything I am bringing near the source charge, right? Source charge I will write Q. Source charge I will write Q or Q naught. To this, near this charge, I want to bring a multiple charges. How many charges I brought? 3 charges I brought. Correct, right? So if you want to bring the multiple charges, you need to do the work done for all the charges. You need to do the work done for all the charges. Each charge will. Yes. No, these charges are, it is not unit charge, positive charges, I am telling. Okay, it may be bigger. Quantity is more, magnitude is more. Okay. So every time you need to do the.
When you take multiple charges, that time quantity will be more.
No. See, to test I taken unit positive charge. But instead, if you want to bring any charge in this case, you need to do work. Okay, just to test I brought a unit positive charge. You can take any charge. So you can take Q. If you want to bring Q near Q naught. Okay, how much work done you need to do means this much. Correct? Since I am taken test charge, that's why it is just 1 Q. If it is some other charge, here it is Q naught into Q will come. Understood? Just I will explain it better way. Just listen. Shall I clear it? I will explain in once again. I will explain. You see, what is the electric potential? Potential due to a multiple charges. Due to a multiple charges. Okay. Fine. Now you see. Here I have one charge, say Q1. Now this near Q1 I will bring one more charge, Q2. Okay. Now what it is Q1 is already there at that position. Now I am bringing Q2 near this Q1. So if you want to bring the Q2 near Q1 from some other place, some very far place, you need to do some work on that Q2. Correct, right? Correct, right? Because this Q1 is already occupied with some field. Correct, right? Now, what is the work done you need to do to bring the charge Q2 near Q1? This work done is how much? Yeah, potential difference between these 2 points. Understood? So this work done is, for example, this is at one point and this is one point. Directly, anyway, we studied the potential value. How much? What is the potential value which is work done? Work done per unit charge is potential, right? Correct? Huh? Work done is equals to work done per unit charge is potential. Okay, that's why work done per unit charge is potential. Now, how much work done you need to do? How much potential you need to apply? The first potential is V1, which is equals to 1 by 4 pi epsilon naught. Okay, Q1 Q2 divided by Q1 Q2 divided by R12. Okay, this is the distance between the charge Q1. This is Q2, which is R12. Understood? So this is the distance. That much potential you need to apply. That is the potential. So work done per the charge Q2. This is per the charge Q2 to bring towards Q1 is V1. Okay. For example, now I want to bring another charge near the charge Q1. So bring charge Q3. Q3 I am bring from infinity to this point. Some point I will bring. This is the one point. Okay, I would like this point as point O and this point as point A and this point as point B. Sure. Now I will bring this charge Q3 from infinity to the point B, which is at a distance from the Q1, which is R13. How much? R13. Some distance is there. And this charge is in the, now it is in the region of field. Correct, right? Now field will act in the opposite direction. I am bringing the charge opposite to the field. Correct, right? I am bringing the charge opposite to the field. Now I need to do some work. I need to do the work. 1 minute. What is the work? How much work? Work done is equal to potential per that charge, which is 1 by 4 pi epsilon naught. How much? 1 by 4 pi epsilon naught? Yes. 1 by 4 pi epsilon naught Q1 Q3 divided by R13. Correct? Correct? Now this is just two charges we discussed. Now third charge you take at point C. which is Q1, Q4, sorry, Q4, yeah? Q1, Q2, Q3, Q4. Now, which is at a distance, how much? Get right, R14. Now, if you want to bring that charge also, you need to do, apply the potential, work done. That work done is stored in the form of potential energy. See, potential energy is the energy due to its position. If you bring the charge from infinity to that point, you are doing work done. That work done is stored in the form of potential energy at that point. That's what it is called potential. Okay. So, Q14. Okay. I think I am doing so much wrongs here. V14 equals to 1 by 4 pi epsilon naught Q1 Q4 divided by R14. Okay, this is the total. So, if I brought how many charges near Q1? Total 4 charges, 3 charges I brought. Now, what is the total potential? V total. What is the total potential? Yes. Q1 plus Q2 now. V12 plus V13 plus V14. Potential is a scalar. There is no direction. Correct, right? It is a scalar. Now, V12 is what? 1 by 4 pi epsilon naught, which is common. I will take outside. Okay. So, it is Q1, Q2 divided by R12. Okay, I will write everything, then I will take now out. Plus V13 is 1 by 4 pi epsilon naught Q1 Q3 divided by R13 plus 1 by 4 pi epsilon naught Q1 Q4 divided by R14. Okay. Okay. Understood? This is V total. This is V total. Now, what is the total final answer? Just take 1 by 4 pi epsilon naught common, with Q1 also common. Correct? Now, it is Q2 by R12 plus Q3 by R13 plus Q4 by R14. Okay, but there is one more thing to discuss. What is that? If I bring this charge Q2 near Q1, that's fine, because no charge was there before, only this charge I brought. Well, I am bringing Q3 towards Q1, this charge was there, no? Correct? No? Even it will also apply force. You need to work even against this force also, right? Why people didn't ask this question?
Yeah, that's what I was going to ask
Yes.
that time, sir.
Correct, right? Whenever I am bringing this charge near this charge, definitely this charge is already there. This also will apply force. That means electric field will act even due to that also. So, you need to do work for that also. What is the work done that? The distance is, how much distance? R23. R23. See, you are not asking this question. Now, you got that point, right, in your mind? Yeah. Now, what is the potential? You need to add that also, which is V32 or V23. Okay. Actually, I didn't take V32 or V23. Plus, one more is this and this. Correct, no? Yes. This and this also will be there, this and this also will be there. You write that also. V34 plus V24. You should add that also. Okay, please write. That also you add. I will write here. V34, which is 1 by 4 pi epsilon naught Q3 Q4 by R34, then V23, which is 1 by 4 pi epsilon naught Q2 Q3 by R23, then which is 1 Q1 3 4 2 3, then 4 3, right? 4 3 done. Only these two, right? V34 V24, yeah, V24 also. V24, which is 1 by 4 pi epsilon naught Q3 2q4 by R14. Please add all that. If you add all that only, you will get this one. I will erase this. Just see, you just see, you just see, you just see. Okay, so I will add this here, right? Okay, which one I want to add? 3, 2. Till 1, 4 I added. 3, 2 I want to add. So 1 by 4 pi epsilon naught Q3 Q2 by R23 or 32. Since it is a scalar, no direction. Next, 1 by 4 pi epsilon naught Q3 Q2 by R23 done right. Now now 1 by 4 pi epsilon naught Q3 Q2 done, Q3 Q4 divided by R14 plus 1 by 4 pi epsilon naught Q2 Q4 divided by R24. Okay, this much big. If you make it small, no, next step it will come. So there is a force between these two also. There is force between these two also. See? Okay. This is R24. This is R34. Distance. This distance. Okay. Understood? Yeah. Now I'll just write here. So V total, okay, total potential V is equals to 1 by 4 pi epsilon naught Q1 is common. 1 by 4 pi epsilon naught. Shall I take in next slide? Okay. Yeah, please take. Is it fine? Then can I take? Yeah. Anyway, you will get in stored video, YouTube. Yeah, live stream. Okay, anyway. Now, shall I erase this? Okay. So, or I will take next slide. Add page. Yeah. Now, what is the total answer we'll get? V total will be equal to V1, that is 1 by 4 pi epsilon naught. That is common I will take. Correct, right? You just see previous slide. 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, 1 by 4, everywhere it is there. Q1, wherever Q1 is there, I will take Q1 common. Understood? Okay. So 1 by 4 pi epsilon naught, Q1 is common. That is Q1 divided by 4 pi epsilon naught. Now Q2 divided by R12 plus Q3 divided by R13 plus Q4 divided by R14. Okay. Next. Plus Q2 1 by 4 pi epsilon naught. Okay. Let's write properly. Actually. Okay. 1 by 4 pi epsilon naught. Q2 Q3 R13 plus 1 by 4 pi epsilon. Anyway, I will common here also. I will take Q3 Q4 R14 plus Q2 Q4 R24. This is the total potential. Okay. That much potential is there. That much work you need to do to bring all the charges, to assemble all the charges in that region. Okay, this is the total potential. Understood? Understood? Yes. So, this is the final due to the system of charges. Now please take the heading equipotential surfaces. So, I will erase this. Equipotential surfaces. Equipotential surfaces. What is equipotential surfaces? Can you please tell? Surfaces, equipotential surfaces. Now you understood what is potential means? What is potential means? To bring the charge, that is there. Potential is the point in the field. It is the point in the electric field where if that point has that stored energy. If you want to bring something to that point, no, you need to do some work. Something means the charge. Correct, right? So, a potential means it is the space dependent. A potential means it is the capacity of that region or the point. If you want to bring another charge to that point, you need to do the work. That work done is nothing but a potential. Okay. Now, I also explained that we need to store the energy. It will store work done, whatever work done you do, it will be stored in the form of energy. Understood? Now, what is the equipotential surfaces? Very interesting. You see, for example, I will take there are electric field lines passing. Okay, electric field lines. Now, I will move the charge. With respect to this, electric field lines are moving in this direction, and I will move the charge from one point to another point. Okay, for example, this is point A. I will move from point A to point B. Okay, these are the field lines. These are the field lines, electric field lines. They are in parallel. They are all parallel. They are moving in one direction, but they are perpendicular to the movement of the charge. Charge I am moving in y-axis, but field lines are moving in x-axis. Understood? So, whenever I want to move the charge from A to B, what is the work done needed to move the charge? What is the work done? Any work done is required? Because field lines are going like this, and I am pushing the charges. Work is? No work done. No, we will push the charge. No force will act. No force. If you want to force, if the charge is experience force, the charge should keep in the direction of the field. This is electric field. Correct, right? Then this electric field apply force. F is equals to Q into E. Correct, right? Okay. So, if I want to just, this charge is there, okay, Q. Then what will happen? This charge will experience a force F is equals to QE. Right?
Sir, if the field lines is coming like this and the charge is coming, only then it will push. If it's going like this.
Yeah. If the field lines are and charge is in the same direction, the velocity of the charge, then it will experience the force. F. Force will act. But I will move the charge in the perpendicular direction of the field. Okay, understood? So, what is potential? It is work done per unit charge. So, when the work done is 0, if it is 0, then what is the potential? 0. In the sense, potential difference is 0, not potential 0. Potential difference, this is delta V, you can write. This is V, potential difference here is VB minus VA, VB minus VA, which is equals to 0. So when work done is 0, then that surface is said to be equipotential surface. A surface is said to be equipotential surface when the work done within that surface is to move a charge is 0. Please write that. An equipotential surface means the potential is same throughout the surface. Right now, the potential is same throughout the surface. Throughout the surface. Please write down. The potential is same throughout the surface. So if the potential is same, then potential difference is 0 between any 2 points on the surface, which is equals to 0. Okay. Now, so if potential difference is 0, means work done is 0. Work done to move a charge. Work done to move a charge from one place to another point, or one point to another point is 0. One point to another point is 0. Is 0. This is what equipotential surface. Okay, you no need to do work actually. The charge it will itself it will go. Okay, in that surface, no, the potential is same. Okay, that is what we call equipotential surfaces. Understood? Understood? Now, one more thing. What properties you can say about equipotential surfaces? If surface, that means constant potential. No different potential. For example, we brought one different multiple charges at one source charge, right? For each and every charge we did work. Correct? No, different work it is. But when the same here at different points we are not doing work only. That is what we call equipotential surfaces. Right? Work done is 0. Any other properties you can tell by looking at this surface? Electric field lines are perpendicular to the surface area. Surface area, how it will be? Area vector, how it will be? I said no. If this is the area vector will be normal. Correct, right? Now electric field lines are perpendicular to the area vector. Okay, that is the second point, you right? Electric field lines are normal to the surface. Which one? No. In field, no, I am just moving in this direction. Field is in this direction. In diagram it will be like you are seeing. This is full field. Okay, this field lines are written. Understood? Charge is I am moving in opposite direction. Normal. What will intersect mean? What it mean intersect? Field lines will never intersect. Field lines will intersect, and charge will be moving perpendicular to the field lines. Understood? And electric field lines are perpendicular to the or normal to the equipotential surface. Equipotential surface. Understood? Understood? Okay, written this one. Now I will take different equipotential surfaces, you see. Yeah. Now you see. Take one equipotential surface, one surface I will take. Okay. This is some charge will be there. Not charge. This is a one surface. Surface A. Okay. Now you see each and every point on the surface. Okay, this is one locus, right? It is not locus, it's like dots. These are equidistant from the point A. Correct, right? They have equal potential. Okay. For example, here one charge is there, for example. Charge is there. This is some field. How the field will be from the charge? What is the field? Direction of field will be always? Yeah, that field lines will always originate from the positive charge. Field lines are always originate from the positive charge. Very nice. You see? Okay. Now, the whatever points I am taking, you see. Now I will write. You see. Now you see. The locus of all the points in that locus, they are at equidistance. They are at equidistance. Electric field lines are like this. Electric field lines are like this. But the points are at equidistance, right? That means the potential of each point is same. Same. Because V is equals to what? 1 by 4 pi epsilon naught Q divided by R. Q is there. Okay. Now each distance of each point from the Q is same. This is R only. Correct? No? Correct? So is in all points are same. This is one equipotential surface. This is one equipotential surface. Understood? Okay. Now for that equipotential surface, what is the direction of electric field lines? There. This is a surface. This is one surface. This is surface. Now electric field lines are perpendicular. Perpendicular, right? This is surface means electric field lines are perpendicular. Understood? Okay. Now I will take one more equipotential surface. You see? Okay. This is having another distance. What is this? You take R dash. This is one more equipotential surface. Correct, right? Now, if you want to again do work, if you want to move a charge from one point to another point, one point to this point, for example, this point to this point, how much work you need to do? See, this is another equipotential surface. This equipotential surface name I write A. This equipotential surface name I will write B. I said it is equipotential surface, and the distance of each point on that surface is same, R dash. Now, what is the question you remember properly? What is the work done you need to do to move one charge from this point to this point or this point to this point on that surface? What is the work done? It is equipotential surface. What is the work done? What is the work done in equipotential surface? Tell. Zero. Work done to move a charge from one point to another point is zero in equipotential surface. Now I am taking, this is a second equipotential surface which is B. Now what is the work done to move a charge from one point, this point P, I will take P, and this is P dash. How much work you need to do? Zero. Correct, right? Now you got on clarity? So this is C. Now this equipotential and this equipotential surface, you see this is one equipotential surface, this is one equipotential. Will they are merged or they are separated? Yes. Equipotential surface never intersect each other. If they intersect, what will happen? It's not possible. Equipotential surface means same potential should be there. If two different potentials, is it possible to intersect? Not possible. It will have different potential. This will have different potential. Understood? So that is the third point you write. Equipotential surfaces never intersect each other. Equipotential surfaces, write down. Equipotential surfaces never intersect each other. Never intersect each other. Done now. Equipotential surfaces never intersect. This is one property of it. Okay. There are like this is you see, for example, you take one spherical surface, a spherical body. The surface of the spherical body is having same potential, right? That is equipotential surface. Whenever charge is there at center. Understood? Now, this is one more point. So 3 points we written. Any other points you? Equipotential surfaces never intersect each other. Equipotential surfaces, work done in equipotential surfaces is zero. Then electric field is always perpendicular to the normal to the equipotential surface. Okay. Any other thing? That's it, right? Okay. So these 3 points you remember, they'll ask in exam about equators. Okay. So shall I erase this? Clean it. Not clean it. Okay. Next, what we can discuss is, I will discuss on one this application, not application. What is the electric potential due to in a dipole? Okay. So please take the heading. This they will ask in your exams. Okay. Electric potential at a point, at an axial or equatorial, you write it. First you take equatorial, then I will do axial. Okay. At an equatorial point, at a point on equatorial line, at a point on equatorial line. Equatorial line of a dipole. Yes. Electric potential at a point on equatorial line of a dipole. Yes. Take a dipole. What is a dipole? What is a dipole? We discussed now what is dipole. Yes, two equal and opposite charges. Two equal and opposite charges separated by a small distance. What is the small distance? 2a. 2a constitute an electric dipole. Two equal and opposite charges separated by a small distance constitute an electric dipole. Understood? Yes, sir. Now, whenever you take a point, this is the center of the dipole. Center of the dipole is O. Okay? Or I can take C. The distance of the positive charge from the center of dipole is, one is A, another one is also A, because it is a center. Now, I will take equatorial line. Equatorial line means what? I explained, right? What is equatorial line means? It will always passes through the center of the dipole. Now, take one point P. One point P. This is point P. Now, what is the electric potential at that point B due to a dipole? The point is at equatorial line. What is the electric potential? Correct, right? Now, if you want to do electric potential, first take the point from the plus Q, you draw, and the point from the minus Q. Okay, so this distance is A, okay, and here it is center, equatorial line. Correct, right? Equatorial line. Now, what is this distance? This is A. This distance you take, the point is at a distance, you take R. The point you take, which is at a distance R. From the center, center C, the point is at a distance R. Okay. Now, if it is R and if it is A, what is this distance? R, A. What is this distance? What is this? If this is R, if this is A, then what is this, sir? R. Okay, AB square plus BC square is equals to AC square. Correct, right? This is R square plus A square. Correct, right? You take one triangle. This is A, this is B, this is C. AC square is equals to AB square plus BC square, Pythagoras theorem. Now AC is equals to under root AB square plus BC square. What is there in this? Correct, right? Now this is under root R square plus E square. Correct? Okay. Now this one is also under root R square plus E square. Correct? Now what is the electric potential at this point P? Due to the positive charge, electric potential is what? V. Electric potential is V plus Q, which is equals to 1 by 4 pi epsilon naught. Correct? No? Q, due to the positive charge, Q divided by R. What is the distance between the point P and the Q? R square plus A square under root. Why whole? No whole square. Okay. Now due to the negative charge, what is the potential? 1 by 4 pi epsilon naught Q divided by under root, same thing, R square plus A square. But negative charge, potential is negative. Correct, right? Negative potential is minus. Now what is the total potential? V is equals to V1 plus V2 or V plus Q, V minus Q. Just add both, what will you get? 0. Because both due to the positive charge also same distance, negative charge also same distance. That's why it is 0. Understood? Okay, please take this. So electric field at any point on equatorial line where the point is at a equidistance from the both the charges is 0. Please write potential is 0 potential is 0 due to a dipole at equatorial point, isn't it? Understood? Yeah. Please take. Now I will do axial also. Make it fast. Finished, Finished, Amma? Make it fast, make it fast. What is the dipole moment? Always it is from negative charge to positive charge. Then now, shall I take next slide? Please take the heading electric potential at a point. Electric potential at a point. Venu, understand here, Venu? You are thinking something? Electric potential at a point on the axial line of electric dipole. On the axial line. Electric dipole. Instead of that, we'll do general point. Okay, 1 minute. Take axial line we can do later. General point. Any general point. at a general point. At a general point. General point. Yes. Due to a dipole. Due to a dipole. Now you see. Yeah. Now you take a dipole. Here I will take negative charge, and here I will take positive charge. Okay. Now you know the distance between the charges, which is 2a. Now the point I will take general point here. General point. Okay. Now the distance of the, see, whenever you want to write the general point where it is, this is, for example, this is a general point P where you need to find the potential. Always we will measure the point from the center of the dipole. Correct, right? So center of the dipole you should take. That is R. R is the distance of the point from the center of the dipole. Understood? Now, what is this distance? This one you take, and you know this one also. This is R1 and this is R2. This is R1 and R2. Okay? The distance between the two charges in an electric dipole is 2a. So definitely you know half distance is a. From the center of the dipole C to the plus Q it is a. From the center of the dipole to minus Q it is a. Now what is the direction of the dipole moment? It is minus Q to plus Q. Okay, you got an understanding? Now what I will do, I need to find the electric potential due to these two charges at one point, general point. What I will do is, I will take the, one parallel line. You can also tell instead of that, 1 minute, you can redraw this, line, you can extend this line. Okay, it's not coming yet. Yeah, this is center. Just extend this line. I will erase this. Oh, bit clear. And it's undo. Yeah, yeah. Now I will just extend this line here. Okay, this is the center of the dipole. Just I extended that line. Okay. Now you see this one. I will connect. This, the path is, I just extended. This is the foot of the path. I will write it as M. Okay. Understood? And here you see. 1 minute. Yeah. Now you see this, the point, no, this point P, which is making an angle theta. The distance between that is making an angle theta. Okay. You can write this also. 1 minute. This I will write 1 minute. Don't be confused. Wait. This is the center. Okay. So what I am telling is, this point is making an angle theta with the horizontal line, dipole axis. If this is theta, this is also theta. If this is theta, now what is this cos of theta? This is, I will write, this is C, this is A I will write, this is B I will write, and this is M. Okay. Okay. A minus charge Q is there, B plus Q is there, and M is the foot of the line which I extended. Foot of the line which I extended. Why I extended, you will understand now. Okay. Now, can you please tell what is cos theta now? Opposite, adjacent. Adjacent divided by hypotenuse, right? Which is adjacent line here? This one, right? This one, right? Correct, no? So, adjacent is equals to hypotenuse into cos theta. Hypotenuse into cos theta. What is hypotenuse? A. This one, C to A. CA. The CA is what? Center of the dipole to charge q. What is the distance? A. Correct, right? Half distance of the dipole. A. A. So this is A cos theta. This extended line is A cos theta. Correct? Okay. Now I will write here it is A cos theta. Now this one you see, the charge at plus q is this. This is R1 and this is R2. Now you see, can you please tell what is the distance R? Distance R here in this line O, AP. See, till here you see, from C to P the distance is R. Correct, wrong? Now this line you see, it is more. It is more, right? So what is the total length of this line? R2. How much? You can in terms of R. Just draw a perpendicular foot. Correct, right? Correct, no? So till this and this are parallel. Correct, no? So till it is R. Now this distance is what? This distance only, this distance, right? Correct? Correct. Now you see the total distance, that is AP. AP is equals to, which is R2, which is equals to R plus A cos theta. Very good. A cos theta. Correct? Now what about this? BP. R1. Correct? Now till here it is R. In terms of R you need to write. Okay? Till here it is R. Now here it is R means, so this is till here it is R means like that it will come, but this there is a small diminish of that line, right? How much it is diminished? This is R minus A cos theta. Correct? You understood why R minus A cos theta? See, this foot you draw, it will come only here up to here, and this distance is same as A cos theta. You write here it is n. Okay, Cn is approximately equal to Cm, because I draw this foot perpendicular line which is touching here. Okay, this touching means this much distance is more in this central line. Correct, right? The central distance Cn is having more distance. Cp is equals to, see here, Cp is equals to, which is R, which is equals to Pb plus Cn. Okay, Pb plus Cn. That's why Pb is how much? R1. Correct? Pb is always equal to Np also. So R1 plus Cn is how much? A cos theta. Correct? In another way also you can write. Don't get confused. So what I am telling is BP. 1 minute. Write it. Don't feel bad. Okay. So what I am telling is this BP. BP is equals to R1, which is BP is equals to R1, which is this plus this minus this. Total distance minus this distance. What is the total? Cp minus Cn. What is Cp? R. R is Cp, no? Total from C to P is R. Minus, what is Cn? Cn is again this is also a cos theta. This is a cos theta. Okay, this is what? BP. BP is R1, which is a cos R minus a cos theta. AP R2 is R plus a cos theta. Now you can write what is the potential due to the negative charge. Minus q is how much? 1 by 4 pi epsilon naught into q divided by what is the distance? This negative charge, what is the distance? R2, right? R2. Correct, right? So you can write R2 is how much? 1 by 4 pi epsilon naught minus q divided by R plus a cos theta. Very good. Correct, huh? This is negative. Now this V plus Q is how much? 1 by 4 pi epsilon naught plus Q divided by R1, right? Now can you please write 1 by 4 pi epsilon naught Q divided by, what is R1? R minus a cos theta. Now both you combine, that is the total potential. Combine, right? Please take. So total R is equals to, sorry, total R I am telling, total potential. Total potential V is equals to V plus Q plus of V minus Q, or V minus Q plus of V plus Q, which is, please combine 1 by 4 pi epsilon naught, you take common, both sides it is there, by Q also can take common, Q is also same, correct, no? So 1 by R minus a cos theta minus 1 by R plus a cos theta, that's it. Just you do the simplification, you will get the answer. Huh? So much variation it will happen, right? If I erase something, I will. Please do it. Make it fast. See, potential is a scalar, okay? That's why we are just adding. If it is a vector, no, it will be different way of adding. You can have vector addition, you know, right? So it is a scalar, just adding, okay? And potential due to this two dipole at general point, it will be different. So can easily you can do. So shall I take the next slide? Yeah, please see. Now what is the total potential? V is equals to 1 by 4 pi epsilon naught. What we got in the last slide? I will write here, which is Q is also common. Okay. Now, yeah, 1 divided by R minus a cos theta minus, right? Minus, right? 1 divided by R plus a cos theta. Now it will be 1 by, so q divided by 4 pi epsilon naught. So r plus a cos theta that side, r plus a cos theta, okay, minus r minus of minus plus a cos theta divided by r minus a cos theta into r plus a cos theta is what? R square minus a square cos square theta. This plus r minus r cancel. What you will get finally, q divided by 4 pi epsilon naught, okay, a cos theta plus a cos theta is 2a cos theta divided by r square minus a square cos theta, cos square theta. Understood? Now, no, this is not minus, this is r only I am cancelling, okay. So it is cos theta minus r, cancelling r. Now, yeah, so it is, what is 2aq? You write 1 by 4 pi epsilon naught. 2a is there, no? I multiply q. 2aq cos theta divided by r square minus a square cos square theta. Yes. What is 2aq? What is 2aq, Venu? Dipole moment. P is equals to 2aq. P is equals to aq. That's why you just write V is equals to 1 by 4 pi epsilon naught P cos theta divided by r square minus a square cos square theta. This is the total potential at any general point. And actually, if you see, if you take any potential, okay, sorry, any dipole, the dipole at any point, the point is very far from the center of the dipole, which is r, but the distance between the center to the charge is very, very less. Actually, an ideal dipole is such that an ideal dipole, the distance between the two charges is very, very less. Okay, it's very small it is. Distance is 2a is very small. 2a is very small. If 2a is very small, a is much more small. But the distance from the center of the dipole to the point P is will be larger, will be there. Okay, better in axial or equatorial. Now, you see, now since it is a larger, no, I can write R is very, very greater than A, so A is neglected. Dipole, the center of the dipole to the charge is neglected. Understood? If you neglect it, what is the potential now? This, if A is small, A square is much more small, so A square is neglected. 0.1 is small, 0.1 square is 0.01, it is much more small, so A square is neglected. So it is V is equals to 1 by 4 pi epsilon naught P cos theta divided by R square. This is entire term is negative. This is the total potential due to the what? Dipole at the general point. Please take it in, write the pen. This is the final answer. Okay? Yeah. Finished? Finished? Yeah. Finished? Now, if you want to, please take fast. Finished only. You? It's recording. Okay, next. Shall I erase this? Shall I take the next slide? Yeah. Now, so this is the topic. Now we have some more things to study, which is, what is the field, what is the potential energy of a dipole, what is the torque acting on a dipole. So many things are there. Okay, in an external electric field. Before that, I missed one concept, which is what is the relation between field and potential? Derivation. Okay, please stay. Relationship between electric field and potential. Electric field and potential. Very, very good, very, very important it is. It will ask in board exam. Relationship between electric field and potential. What is the relationship? You know, actually I explained. Okay, but I will do derivation now. I will take two metal plates or two surfaces, okay, of different potentials. Two surfaces I will take. Two equipotential surfaces I will take. So one surface is having equipotential surface means, you know, right? Any surface which has same potential. Like the two different plates I will take. I mean two surfaces I will take. First surface it will be like this. This is the first surface having the potential V, equipotential surface. What is the potential? V. Yeah, this is V. V. Now another surface. This is another surface having the potential V plus dV. No. This is one surface. This is another surface. This is equipotential surfaces. Both are equipotential surfaces. Equipotential surface means that surface is having same potential. This surface is having different potential. Okay. Any point on the surface is having same potential. So these two are the surfaces. Now, since these two are the two surfaces, I will move the charge from one surface to another surface. I want to move the charge. I will move the charge, this surface I will name it as A. What is this? Yeah? This surface name it is surface A, this surface is B. Okay. Now, what I will do, I will move one charge from this surface to this surface. Okay? Like this. Yes. This I will move a charge from one surface to another surface. Understood? Understood? So, if I want to move a charge of Q, the distance between the plates I will take it as R. Okay. Distance between the plates is R. Now, for example, if I want to move the charge from higher potential to lower potential, or from lower potential to higher potential, which one is chosen? If you want to move from higher potential to lower potential, it is why? Yeah? Easy, right? But lower potential to higher potential means stuff, because higher potential will give maximum electric field. Lower potential means less electric field will be there. So if you want to move a charge against the direction of electric field, then you need to do more work. Correct, right? So the work done to move a charge, I will write here, the work done to move a charge from higher potential, lower potential you take. From one plate to another surface you take. One surface to another surface. From one potential surface to another potential surface to another surface, potential surface is, another surface is how much? W is equals to how much? Work done. Ah, what is work done formula in terms of potential? Tell. Work done is charge into work done per unit charge is potential VB minus VA. Sir, VB minus VA or VA minus VB. We are bringing a charge from lower potential to higher potential. Correct, right? Again, from this plate to this plate. We are moving a charge, right? Which is higher potential, VB. This difference is potential difference. See, how many times I said the relation between charge, work done per unit charge is what? Potential, right? Okay, so work done is what? Charge into potential. That potential is different, no? That's why it is delta V I take. Correct, no? That was same formula I applied. Why you are getting confusion? Now, can you please tell? So this is W is equals to Q into VB minus VA. This is number 1. This you know. Okay. Now, what is the relation between the potential and field? Potential and field. If potential is there, means exactly field will be there, right? What is the relation between potential and field? Field lines will act, right, in the opposite direction of the moment of the charge. Charge will move from here to here, means it is moving against the direction of field. So what is that? What is work done per moving a charge? Work done is equals to, in terms of field, tell. Okay, so work done is force into displacement, right? Work done is force into displacement, correct? You agree for this? Displacement I will take R actually, so I will take here it is R. Oh, sorry. Here it is I taken R, so I am taking R, F dot R. Okay. Now W is equals to F into R, and work done is which is, what is force in terms of field? F is equals to QE dot R, but it is in the direction is opposite to the electric field, that's why it is negative. Understood? Okay. Work done is, see what I am doing is simple one. Work done is equals to what? Force into displacement. Work done is equals to what? Force into displacement. F vector dot R vector is W, if you want to take that vector form. Now force is Q into E, and R is the displacement. But whenever you do the work, no, whenever you want to move the charge, you are moving against the electric field. This is one plate means it is having some potential, means potential is there, means electric field lines will be moving like this, means you are moving a charge which is against the electric field. Q is moving with this velocity, some velocity or moving. Then what will happen? You need to do the work. That's what I am doing. So Q into E into R. This is the equation number 2. Correct? Now from 1 and 2 work done is same. So from 1 and 2 what you will observe? Minus QE into R is equals to what? Q VB minus VA. Correct? Q cancel. What finally you got? E is equals to this negative sign, you bring that side, which is VB minus VA divided by R. This is the relation between electric field and potential. So electric field E is equals to minus delta V by R. 3-mark question. You can explain it different ways. I taken 2 potential plates. Okay, you can also explain in the single axial line also. This is easy. So what I am doing, once again I will tell, This is one first plate, this is second plate, this is having a potential V, this is having a potential V plus dV. So there is a potential difference. What we should do? We should bring a charge from first plate to the next plate. If you want to move a charge from one plate to another plate, what you need to do? You need to do work done, because there is a difference in potential. So what is the work done? Q into VB minus VA. We also know that if we do the work which is against the electric field, okay, because potential is there, means field lines. If we studied in equipotential surfaces, what is the property of equipotential surfaces? Electric field lines are always perpendicular to the normal to the surface of the equipotential surface. So they are normal. Electric field lines will be somewhere like this, they are going. Now charge, I mean the point charge I am bringing from here to here, one plate to another plate, electric field lines will be like this. That's why work done we are doing, which is Q F into R, force into displacement. Force is Q into E into R. Just combine both, you will get the answer. This is easy. Okay, please take this. Very, very important. Yeah. What's the time now? Thick. Finished, huh? Take fast. Yeah. Next. Shall I erase? Clear? Or next slide? Yeah. Next thing is potential energy of an electric dipole. Okay. Potential energy of an electric dipole when a dipole is placed in presence of electric field. Okay. That is the next point. Please take potential energy of an electric dipole potential energy of an electric dipole when we placed a charge in presence of electric field lines. This is a random discussion I will do. Just see. Now you take a dipole. Okay. I will take a dipole which is negative, positive charge. They are the equal and opposite charges separated by a distance 2a. Correct, right? This dipole I will place in presence of electric field lines. Electric field lines are going in the which direction? You know? Which direction? Right, left to? Right. So I am placing, these are the electric field lines are passing, and I am placing a dipole in the middle of the field lines. Understood? Whenever I place a dipole, now what happens? Will the dipole affects? Why? Yeah. Okay. Now what I will do? I will just touch this dipole. I will just rotate it in anti-clockwise direction. Just a small rotation I will give. This is the center of the dipole. Understood? Just I will rotate it. This is positive charge. This one is negative charge. Okay. Just what I did? Tilted. I just tilted by some force. Now what will happen to the force on the charges you find? What is the force acting on the positive charge? F is equals to, what is force on a charge? F is equals to Q into E due to electric field, no, plus QE. So electric field lines will act on a charge. They will produce some force on the charge. Whenever charge you keep in the presence of electric field, what will happen? It will apply force in the direction of field. See, direction of field is this side. So what happens? Charges are kept, it will experience a force F is equals to plus QE. And I will tilt the this one with theta 1. With theta 1. This is the angle I tilted the dipole. I just move the dipole little. Now, what is the force acting on the negative charge? F minus Q, which is equals to what? Minus QE, right? I will write this properly. F is equals to minus Q into E. Which direction? This direction. Always remember, positive charge will always move in the direction of electric field. Whenever electric field, this is a charge, this is a dipole, this is positive charge and this is negative charge. Whenever electric field lines are going like this, okay, this positive charge will move in the direction of electric field. This positive charge will experience a force in the direction of electric field. This negative charge will experience in the direction opposite to the electric field. Electric field is in this direction, but this negative charge will experience force in the opposite direction. Understood? Now, for example, this is the electric dipole. Electric field is going like this. Now, what will happen? This is positive charge. Positive charge will experience force in the direction of electric field. Okay. This negative charge will experience in the direction opposite. That's why it will rotate like this. Understood? Okay, not completely. Just this is for example, electric field is coming in this direction. Now how it will rotate? It will rotate like this. Okay, this positive charge will try to move this side. This negative charge will try to move this side. So it will, correct, right? Correct, no, this side. So it will go like this and this will go like this. So yeah. Now if it is like this, no, sorry, it is like this, electric field is like this. This will move in this direction, this will move in this direction, this will move in this direction. Understood? Okay, that's why whenever it experience force this side, it experience force this side. Now what is the direction? No, how it will tilt? Okay, I tilted the dipole in anti-clockwise direction, little bit. So it will experience force. Now what is the direction of the dipole? Whether it is clockwise or anti-clockwise? Because it is positive charge is force is acting that side, negative charge is this side. Now what will happen? It will again tilt to clockwise. Understood? Understood? Now I will, for example, I will tilt this till like this, plus Q. Okay, this is negative, minus Q, negative charge. Okay, this angle I will tilt till theta 2. This is theta 2. I tilted completely 90 degree, perpendicular to electric field. Correct? No. Now force is, this is on this side and this will be on this side. Correct? Now? Now it will, what it will do? It will tilt to clockwise. I tilted in anti-clockwise, but after the application of electric field, it will tilt to clockwise. Understood? Understood? Yeah. Now what is the potential energy? U. What is potential energy? U. U is equals to what? Work done only. Potential energy means work done only. U. This I will write du, which is equals to work done, which is F into, no, wait. Okay, F vector dot dr. Here not dr. What is there here? d theta. D theta. Correct? This is same as work done, no? So, yeah, even energy is equals to F into d theta. Understood? Okay. So, du is integration, you do integration of du is equals to integration of F into d theta. Now, it is moving from initial energy. You take, it is u1 to u2. What is u1? See, for example, now I tilted complete like this, then again it is coming back. Initial energy is u1, initial potential energy. Now, finally, it will tilt because of the electric field. It is u2. Understood? Initially, I will keep like this. Again, because of the force, what will happen? It will tilt. Okay, u2. Now, theta 2 is initial I put, then again it will rotate to theta 1, for example. That is, okay. So, this is u2 and this is u1. This one is theta 1 and theta 2. Correct? Now, can you please tell what is integration of du is u. Integration of du is u from the limits u1 to, from the limits which is u1 to u2, which is equal to, I am sorry, here there is no space, I will erase here and I will write here again. You see, here I will write integration of du is u, which is from u1 to u2, which is equals to integration of f d theta. F you take out, okay, integration of d theta will be there. Okay, first what you will do is then you just substitute f d theta. Sir, there is one problem here, sir. Here force is acting. Here force is acting and the body is rotating. Now, if in the rotational motion, what we will call that force? What we will call that force? We will call it as torque. Correct? Now, force is in translatory motion, torque is in rotatory motion. So, instead of F, what you need to take? Torque. This is torque. Tau d theta, tau d theta, tau. Understood? This is from theta 1 to theta 2. What is torque, man? Yeah, torque is equals to F into F for sine theta, right? Torque is a vector. So, it is F into R is what? A. Correct? No? F A sine theta d theta. F A sine theta d theta, which is u1 minus, this is u2 minus u1. So, u take upper limit first minus lower limit, which is equals to torque is force into displacement. Force into displacement is F into A sine theta, because tau is always, you can write, okay, 4 F vector dot A vector. Why A sir here means distance from the center to the charge. Correct? No? See, axis is center. Understanding? Understanding? Listen here, listen here. This is tau and d theta, understood, right? Now, what is this tau? Make it silent. I will write that side then. Now you see. Okay, u from u1 to u2 is there, which is equals to integration of tau d theta is there from theta 1 to theta 2. Now, what I am telling is, instead of doing direct integration, once again we will do, together we will do. What is this tau? Tau is equals to what? Torque is equals to F vector dot R vector. Force into displacement is torque. Okay, force into displacement is torque. But F vector dot, what is the displacement here? Distance between the center to the charge, A. A, distance from the center of the torque to the charge, A. So, that is FA, F vector dot A vector. Now, what is F vector dot A vector? Dot product means which one will come? Torque means not dot product, cross product, because it is a vector. So F vector cross A vector is FA sin theta. FA sin theta. Substitute this here, then what you will get, U from U1 to U2 is equals to, directly I will write apply limits. So you just see how I can apply limits, you will understand. Okay. So take first upper limit in the place of U, which is U2, minus lower limit U1, which is equal to integration of from theta 1 to theta 2 F A sin theta d theta. Okay. This FA take out, F into A, integration of sin theta d theta. Theta 1 to theta 2 sin theta d theta. What is integration of sin theta? Right. Okay. So F is equals to QE, correct? A sin theta d theta is minus cos theta from theta 1 to theta 2. That you need to do is, what you need to do, you need to apply limits. Just write down, write down. The total distance we need to take now, dipole, no? Total distance, this is not just A, this is 2E. This is 2E. 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 This is 2E. F into 2E. Now 2QE will get. Okay, because total distance you need to take for a dipole. Sorry for that. Here force into displacement, no. Now we both are moving, right? So F into displacement is 2A, F into 2E. Now F is equals to Q into E, 2QEA. Understood? No? Understood? Not understood means I can explain once again, no problem. Yeah. Shall I erase this? Or shall I take next? Next I will take. Now what we got? Tau is equals to, sorry, not tau. U2 minus U1 is equals to how much you got? F is QA, I said, no? QA, sorry, 2QA, 2QA. You see, what we got is integration of, I will sorry, once again I will explain here, you see, integration of tau, okay, into distance is 2A, I am only forgetting, yeah. Why it's not moving? Hanging, huh? Okay, I will just see, I will show you back previous later. What you got? 2QEA, correct, right? Now you see. 2QEA minus cos theta from theta 1 to theta 2. Now you take first, minus is there, no? Whenever minus is there, my logic is take from lower one to, don't take upper one, take lower one. What is the lower one? Cos theta 1 minus of upper one, cos theta 2. Take, if negative is there, if otherwise no sir, I am confused means you take cos theta 2 negative minus of minus plus cos theta 1. Same thing you will get. So 2 minutes. That will become, what is 2AQ? What is 2QA? Dipole moment, P. PE cos theta 1 minus cos theta. This is U2 minus U1. Till this much you remember, tomorrow we will do the rest of this. Okay? This is the potential energy. Thank you. think I've taken so much time. No? Yeah, this is God charger is gone. Yeah, yes, sir. How much time, sir? 1 hour 36 minutes. Oh. So it will be there in YouTube, right? Actually, today's topic is confused.